Alright, hi everyone. So today we're finally going to prove the uniqueness of factorization of ideals in Dedekind domains. Okay, so we're going to prove the following theorem. This is the 30th one, so this is going to be 30.1. Theorem. Let A be a Dedekind domain. And let's say A is a non-zero ideal. Then there exist unique prime ideals. Maybe I should say, I'll just include this proper. You can adjust the statement to include the unit ideal case, but if I'm going to be precise, I need to be a little more careful. There exist unique prime ideals. Let's say P1 to PR. And integers, I guess, yeah, integers. E1 through ER. Each of these strictly greater than 0, such that this ideal is the product of these primes to the given powers. PR to the ER. Okay. So there's kind of two conditions, two pieces to this. There's an existence piece and a uniqueness piece. So for the overview of this lecture, we're first going to prove the existence, and then we're going to prove uniqueness. Okay. So let's go ahead and get underway. We're gonna recall the lemmas from last time, from lecture 29. 29.1. Every ideal in A contains a product of prime ideals. Since A is a Dedekind domain and Dedekind domains are Noetherian, 29.1 says every ideal in A contains a product of prime ideals. Okay, 29.2 says essentially that powers of coprime ideals are coprime. I guess it really says that powers of coprime ideals are coprime, but given two distinct prime ideals, these are necessarily coprime. Powers of prime ideals are coprime. And 29.3 is going to tell me that A mod P is isomorphic to A. Remember, A again is a Dedekind domain, so each of these prime ideals are also maximal ideals. So I can use 29.3 to give me this isomorphism. Okay. So these are three lemmas that we're going to use in the proof. Okay, so we're going to let A be contained in A, be a non-zero ideal. by 29.1, A contains some product of prime ideals. Let's say P1 to the F1, PR to the FR, where these are all distinct, the P's of I are all distinct prime ideals, and Fi, these are all, say, greater than 0. Okay. So by the second lemma, by 29.2, the collection here of Pi to the Fi, these are all pairwise coprime. So what we're going to do is we're going to use the Chinese remainder theorem. By the Chinese remainder theorem, A mod P1 to the F1 PR to the FR. This is isomorphic. So since these are all pairwise coprime, I can split this up into a product of rings. Okay, and the basic idea for the rest of the proof is as follows. So I'll just explain it in words. Ideals in a product ring are product of ideals. Each of these are isomorphic to these quotients of local rings, or like, each of these is isomorphic to some quotient of a local ring. These local rings are local Dedekind domains, which are then DVRs. And then I know what ideals in a DVR look like. I can lift ideals here to ideals here, and then a product of ideals here lifts back to an ideal here, and is going to then tell me what my A looks like. Okay, so our ideal A corresponds to some ideal in this quotient ring. So since A contains this ideal, to an ideal in this product ring, and I know by maybe my 5th lecture, ideals in this product ring are products of ideals. Let's say I1 cross I. This should be an R. There should be no S's. Okay. I sub j, subset of this thing. An ideal. Okay. Now, you can check the following. Our isomorphism here A mod P isomorphic to A P mod P A sub P descends to an isomorphism A mod P to the F isomorphic to A localized to P mod P to the F A localized to P. So you can check pretty easily that you get an isomorphism here, and ideals in this ring. So recall that localizations of Dedekind domains are again Dedekind domains. Okay. So we prove this maybe in our second lecture on Dedekind domains. And more recently we proved that these are, and local Dedekind domains are DVRs. So this is what all that legwork was for. It was basically this sentence: local Dedekind domains are DVRs. So ideals in A localized at P. So our classification of ideals in DVRs every ideal in A localized at P has the form P to the E A sub P. Okay. What does it tell me? So ideals in this guy here, these correspond to ideals in A localized to P containing this thing. Okay. So what do we see? The ideals in A localized to P containing P to the F A sub P are of the form P to the E A sub P with E less than or equal to F. Okay. What does it tell us? I sub j corresponds to an ideal here. This tells us that. So translating through these isomorphisms. And I realize I could be a bit more careful here, but I think basically if this is ambiguous to you, then it would be a useful exercise to write down these isomorphisms and expand exactly what I mean by translating here. Translating through these isomorphisms. We see I sub j is necessarily P sub j to the E sub j with E sub j less than or equal to F sub j. Okay. So ideals here correspond to ideals here. I know what every ideal here must look like, so I know what every ideal here must look like. Now, once I know this, then I can translate through my previous isomorphism. Okay. So, thus, A corresponds to P1 to the E1, PR to the ER, contained in A mod P1 to the F1, PS to the FS. And then by the correspondence between ideals in the quotient and ideals containing the ideal you're quotienting by, I think maybe by the correspondence theorem, I think is just what this is called. A equals P1 to the E1, PR to the ER. Okay, so this proves existence. Okay. So once we have all these lemmas in hand, this existence proof isn't that bad. I will say there are, I guess, there are sentences here that are like technically multiple steps, like looking what happens through isomorphisms. But this is basically, you could, if you understand what's going on here, you can expand out these sentences without basically thinking at all. Okay. So this proves the existence. Now we turn our attention to, so yeah, I guess maybe let me just give you a brief overview of what we did. Okay, so to prove that A factors as a product of prime ideals, first I found a product of prime ideals contained in A, and then I know A corresponds to an ideal in this quotient. This quotient is a product. I can determine what ideals in these products, or in each factor of this product looks like, using the structure of a DVR, and then that lifts back to what A looks like in this quotient, and then I can lift all the way back up to A using the correspondence theorem. Okay. So next we're going to turn our attention to uniqueness. Okay, and the way we're going to prove uniqueness is kind of confusing at first, at least it was to me. We're basically going to prove that these E's are completely determined by A. So we show if A equals P1 to the E1, PR to the ER, then A times A. So if I look in the ith, I look at the ideal generated by A in the ith localization, and this is going to be Pi to the EI AP. Okay, and this suffices to prove this because basically this tells me that from A I can determine all these powers. If I got two different powers, so if I got two different factorizations, then I would have to get two different powers, which would force two different powers of P to be equal in the localization, but this can't happen. Okay. This can't happen because, so if B to the E AP equals B to the E prime AP. Well, these are, AP is a DVR, these are local rings. This means that pi to the E equals U times pi to the E prime, which is, so basically, if, let's say E is less than or equal to E prime, we can assume this without loss of generality. Let me go. Okay. Then I can I can use cancellation to get that pi to the E minus E prime equals U, but if pi to some power is a unit, then E minus E prime has to be 0. Okay, so by looking at this ring, I can completely determine the powers of every prime dividing A, which means that it can only really have one factorization. Okay. So it suffices to show basically it suffices to show this claim. Okay, now how do we do that? Well, one inclusion is pretty clear. the fact that the other conclusion is a little bit more work. The fact that this guy is contained in this guy just follows from A contained in P, I. So since each of these ideals, this product is contained in Pi to the EI for each of these i's. Okay, so one inclusion is clear. We're going to let A over S be in P to the E. Is P. Here A is going to be in A is in P to the E, and S is not in P. Okay. So since all these prime ideals are distinct, we can find an element, choose Si and I guess maybe Sj, and Pj, kick out Pi for I not equal to j, and we're going to let capital S be the product of all these guys, where I obviously don't include Si because I haven't even defined it. Okay, and notice that this big capital S is not in P since P is prime, and each of these Sj's are not in Pi. It's prime. Okay. So we're going to let E be the maximum power that appears. This should be Pi. And again, since S is not in P, this capital S to the E is not in P as well. Pi. Okay. We see well, since A is an A and A is an ideal, there's mathfrak A. Okay, we have this, and what can we say here? A over S equals A times S to the E over S times S to the E, and this is in A. Okay, so we took an arbitrary element of Pi to the EI times A sub P. Oh, what am I saying? Oh, okay, sorry. I need to be more careful about why this element is in here. A is in Pi to the EI. S to the E is in, so this is in Pi to the EI, and this is in P1 to the E1. Basically everything except for Pi to the EI. PR to the ER. Okay. And so when I take the product together, I get something in the product of all these prime ideals, which is necessarily an A because A is the product of these things. Okay. And now I get this containment. Okay. And that finishes the proof of uniqueness. So to prove uniqueness, essentially, you can determine the power of any given prime ideal just by looking at the ideal A generates in the localization. Okay, and we're actually going to use that. So this this formula here will be useful in the future. Okay, so using the structure of ideals and DVRs and the structure of Dedekind domains, we prove that ideals in Dedekind domains factor uniquely. Yeah, so this is some way of salvaging unique factorization from the integer case. So the kind of goal moving forward is to look at how ideals factor in extensions of Dedekind domains. So we'll talk about that, and that has some useful applications for looking at how given prime ideals look in number fields. And then we'll kind of move on to the class group from there.